All right, so we've just kind of gone over periodic categories. Now let's go over periodic trends. But before we do that, I need to introduce a concept known as Coulombic attraction or nuclear effective charge. Coulombic attraction is a terminology that we can go across disciplines. Nuclear effective charge is specifically from the chemical perspective of the application of Coulombic attraction. All right. So, oh no. Okay. So, the idea is that Coulombic attraction is the discussion of positive and negative attracting one another, right? Opposites attract. Okay. So, when we take it from a chemical perspective, nuclear effective charge, how effective the nucleus's positive charges at pulling in things, at attracting the electrons, we say the more protons, the more effective nuclear charge. However, the farther the distance, another way of putting that is the higher the energy level, okay, the less effective nuclear charge. The less effective your nucleus with your protons in there are at pulling in the negative electrons that are attracting them. Okay. So the equation for effective nuclear charge versus Z, remember Z is atomic number, which is proton charge, EFF, effective, okay, is Z atomic number, proton number, minus your screening electrons, the electrons that block whatever series of electrons you're looking at. So if you're looking at the valence electrons, all those core electrons would be considered screening electrons. They block the other electrons from experiencing the positive attractive pull. Okay. So this, by the way, explains why when I messed up yesterday in the lecture, okay, this explains why the 4s orbital is at a lower relative energy level than the 3d orbital. It's because the 4s orbital is circular, it's chunky, and that chunky, right? More of them to love, right? That chunky nature blocks the 3D 10 potential electrons that are actually shaped like a 4-leaf clover that have to penetrate to get into their access to the nucleus. It blocks them from experiencing the positive charge of the nucleus. So that's why we see, relatively speaking, that the 3D orbital is slightly higher energy farther away than the 4s, even though overall energy level 4 is still higher energy farther away from the nucleus.
Suspicious stain again.
We'll keep it for now. That's a fractional distillation tube with a sidearm. Okay, so that is one of the most common FRQ explanations when you're talking about why do we see certain things be higher energy than the other. Nuclear effective charge. That is one of the most common FRQ explanations when talking about trends with protons and neutrons, or sorry, not neutrons, electrons. Okay. So, and then here's a little picture. Watch my amazing art graphics. My sister is actually quite grafted. Shout out to Maria. If you're ever watching this, she wouldn't watch it. She doesn't care. If you ever get to go to Westmont, where my alma mater is, she does art pieces beautifully. But here's the 4s. Let's say this is 4s. Okay. This thing, chunky bunky. Okay. The 3D, even though it's technically at a lower energy, the 3D shaped like a 4-leaf clover, all the electrons in the 3D are getting blocked by the electrons in the 4s. That's why you see that the 4s electrons demonstrate a relatively lower energy, more stabilized energy, closer to the nucleus, okay, in your electron configuration. The actual formula for calculating the Coulombic attraction force is this here. It's some Coulombic constant that I did not discover. Nothing. I've discovered nothing. And particle times the particle charge. So like if you have one positive and one negative or whatever, so forth, the relative charge of your particles in coulombs all over your radius squared, the distance between them. Notice, distance exponentially weakens the effective nuclear charge compared to the charge boosting it. So that's something to consider. It's kind of like, this is one of my favorite analogies, kind of like long distance relationships. I don't care how much fire and charge and passion you have in your relationship. Long distance is really, really hard. There's something powerful about distance, right? So, okay. So anyway, affected by charge, okay, increases Coulombic attraction, but distance exponentially decreases Coulombic attraction. Ca. Put an I in the middle, CIA, but we're, yeah.
What's it called nuclear effective charge and not just effective charge?
Because it's in the nucleus has the protons that are positive that are pulling. The protons are like the muscle of the pull. The electrons are kind of just there for the ride. Yes, I saw a question go up. Hand to go up. No. Sorry, do you have a question?
No, I don't.
Oh, okay.
So like theoretically, the electrons obviously don't matter until the ring, like, until there's another outside ring.
Huh?
Does that make sense? The protons. Like,
Yes.
adding the more protons is more powerful than your
Right,
literally the
until you
electrons
get to the
being
next
added
ring.
until you get to the next
Yep.
ring.
Yep. Excellent. Very good job. Okay, so go ahead and do these this quick practice problem. Right here, 1 through 4. 1 through 4. Do that on your own. Okay, so practice problem 1. Which atom is experiencing a stronger Coulombic force overall? Sulfur. Sulfur. Selenium is in a whole nother energy level. So you get a exponential.
There's like a
Okay.
whole lot other
Go
components.
around. Bye. Okay, sulfur. How did you know? Because sulfur is in, or I could put it this way, the max electrons are placed in the max row or energy level of n equals 2. But selenium, okay, is in n equals 3. So its valence electrons, it has more electrons experiencing less overall, okay? An atom with more protons will have, Alec.
Since most are disregarding energy levels in general, the few orbital shells have a constant radius towards the center neutron, or is the Coulombic force variable across the orbital?
Well, each relative orbital does have a relative radius, but if you actually look at the orbitals, they're technically waves, so they fluctuate. Okay, yeah.
Comparing like the elements here and like
Mm-hmm.
when will the number of protons, like let's say, when will the number of protons matter more than
When I give you actual math values and you use the equation, but I won't, and neither will the AP.
that will never happen.
Mm-mm.
So it's just always
Yep.
with the orbit.
Yep. Or you make an educated argument.
And the S ring is more stable than the D ring.
S
The S
orbital
sorry,
orbital.
is more stable than the D orbital.
Yes, for a respective energy level. Mm-hmm. Yes.
When we talk about how the electrons can't go close to the nucleus or addressing the orbitals, does that mean that the orbit just, like, what happens to the electron when it's trying to get to the closer end of that orbit? It's not
It just kind of stays in its zone.
that little like end of the leaf, it just fluctuates in there, or
Sure. I mean, it's a wave, the wave probability spectrum, technically. So if you think about it too much like matter, you miss a lot of it. But if you think about it too much like energy, you miss the matter. So you're both yes and. Okay, so an atom with more protons will have A or B. A, more Coulombic attraction. Why? Because more protons, okay, results in greater charge and thus greater Coulombic attractive force. Okay, so because of this concept of Coulombic attraction, we get 4 to 5 main trends on the periodic table. 4 to 5 main trends. The first trend is atomic radius. Okay, atomic radius is one of the first trends. All right, and it tells us that one, atomic radius is the distance. This should seem quite obvious. From nucleus to valence shell, or outermost energy level occupied with electrons, right? Valence shell. It's usually measured in picometers. Picometers times 10 to the negative 12th, okay, meters. And we say that across a period, across a row, we see it decreases, okay? And, oops, I wrote that a little high. Yeah. Across a row, it decreases. Why? Because as you go across a row, you increase your proton count, and therefore you increase your Coulombic attraction, which makes the force of the pull in stronger. So that means you pull in your electrons tighter, right? That's a rhetorical right. So the group trend, down or up a column, however you want to think about it, I'm going to think about it down a column. Your atomic radius gets larger, okay, down a column. We're going to do down a column. Why? Because you now have an increase in energy level, which results in a decrease in Coulombic attraction, which results in a decreased ability to pull electrons tighter. Yes, Alec.
What is counteracting Coulombic attraction when dealing with an atom? As in, why do electrons just sit into the nucleus if there is a force that's pushing them that?
Well, the electrons repel each other too outward. Other electrons repel each other. And there's also another, there's like the forces of the world, of the universe. It kind of creates a balance. And if they're constant orbit as well, they'll never fully cave into itself, or else you'd create a black hole in an atom, which would be very bad. Very, very bad. Yes. Yes, please do. Do you need a charger? Okay. So, cookies? Cookies? Yeah, cookies. They're my favorite cookies. This is on recording. They're my favorite cookies. They don't even count as calories. Just joy.
They kinda do actually count as calories.
Health class, right?
Health
Yeah.
class would actually say that.
By atomic radius before the time 10 to the negative.
PM, picometers.
I know, but is that supposed to be a 1 or a parenthesis?
It's a parentheses because I assume that you know it's a 1. There's a 1 in front.
Oh,
It's just trying to tell you the scale. Okay, so how does this also affect now? There's a general trend that you will want to memorize. Common MCQ question, FRQ question. What about ions, charge, right? When we mess with electron count, what happens? Generally speaking, a cation is always smaller than the neutral form. Because generally speaking, if you remove an electron, especially if it goes down in energy level, you no longer have electrons in a higher energy level, you're going to have more protons to electron ratio, creating a tighter pull. On the other hand, an anion is generally larger than its neutral form.
Larger in terms of radius?
Yes, in terms of radius, than its neutral form. Again, especially if you have an electron that's jumped up to the next level, you just exponentially decreased one electron's experience of the nucleus.
The electrons matter now because the proton count is changing. so the
Yes.
electron count-
Excellent. So go ahead and do the practice problems across the 2 pages. It just should take you about 30 seconds. Okay, so practice problem 1. Which one has a larger atomic radius? Neutral boron. How about 2? Negative fluorine. Joy, would you like a cookie? Okay, so electronegativity now. Let's move on to the next category of trend, okay? These are all characteristics that we see for given atoms that we are able to predict now based on the pattern and organization of the periodic table. The way it's set up allows us to make a prediction in these characteristics. What do we see about these characteristics as we move across and down? Or if you want to put it the other way, backwards and up. I don't know. I don't care how you look at it. Okay. Electronegativity is the ability, okay, of an atom to attract electrons to itself in a bond. That is the key clausal phrase right there. In a bond. In a bond. Okay. So across a period, we see that electronegativity increases, right? Which would make sense because you have more protons, you have more Coulombic attraction. And if you're really good at holding in your own electrons and you're in a bond with somebody else, the likelihood is that you're also going to suck in somebody else's electrons as well, especially if you're already connected. And so that means you're going to be really good at easy to attract other electrons, right? Now down a group, okay, we see it decrease. Okay, you have higher energy, okay, higher energy levels. That means your Coulombic attraction is going to weaken. That means it's going to be harder, decrease, okay, attraction of other electrons in a bond. You know, when you're around people, dare I say I'm one of them, don't jokes. Okay. You know, when you're around people that are just like super charismatic and they just seem to like have people come to them and you're like, how do people make such friends so easily? They more friends, like the people that can make friends just seem to constantly gather more friends because they almost seem to have this attractive force on them that pulls people in. So a friend on the fringe will suddenly become friends with them. And you're like, hey, I introduced you guys. Don't be better friends than, right? But you know, you meet those people, it's the same idea. Okay. There are just some people, there are some atoms out there that are just so good because of the Coulombic attraction, attracting their own that are near them, that it's easy for them to pick someone else up in the process. Okay. And then there are some that aren't. Okay. So we'll leave it at that. Try the practice problems 1 through 4. For the first one, shout it out, A or B. A. For the second one. B. For the third one. B. For the fourth one. A. Excellent. Moving on. Okay. So ionization energy is the next characteristic. It's the energy required to remove an outer electron. A valence electron is another way of putting it, from an atom. So this is basically the energy that a thief would have to put in to steal your electron away. All right. Ionization energy sounds a lot like electronegativity, the ability to attract. But here's the difference. Ionization energy is not in a bond. It is not already in a bond. It is literally coming swipe or no swiping, okay, Diego level, or what is that, Dora level, okay, of the fox, and coming to try to take one, creating an ion, by the way. Ionization, ion making, removal of an electron, ion making, yes. It is not, but that is okay. No, it is not. But that's actually a really good thought. I mean, to a discrete level, no, it's not. Let's just say it's not. So, periodically wise, okay, ionization energy increases across a row or period. It has the same trend as electronegativity, but different meaning. Why? Again, okay, I'm just going to little circle, okay, and copy and paste. But instead of saying easy to attract another electron, it just makes it really easy to steal. Oh, no, I'm wrong. Do you feel how that's wrong? Do you see how that's wrong? It makes it really hard to steal. So you're going to have to put in more energy. So you're going to need to put in more energy required. Nobody caught that? Okay, that's totally fine. More energy required. Higher ionization energy.
So the first was like how easy it is to take, or hard it is to take other people's electrons, and this is about if you could keep your own electrons.
You could think of it that way. You're technically reversing it, but you can think of it that way. Okay, so down. And I think the other one I should have put that I'm going down. Okay. Ionization energy decreases. For the exact opposite reason, you have sorry, I just scared myself. Copy, paste. You have more energy levels. I'm going to say EL, more energy levels. So you're going to have weaker Coulombic attraction, which is going to make it easier to steal. And it's going to therefore require less energy. Okay. So these trends are very popular concepts in the AP. Okay. So when you look at ionization energy, we can actually have successive ionization energies because we can just keep peeling electrons away. It's not favorable, but we can. You'll notice that every time you increase, you successively take another one away, it gets more and more difficult. Why? Because every time you remove an electron, you get a greater ratio between your protons and your electrons that are remaining. So every successive electron removal, okay, is more and more unfavorable, unfavorable. And what you're going to see soon is that it's particularly unfavorable when you remove an electron that is making up an octet, that is the 8th electron in the s&p orbital. It's particularly, really, okay, unfavorable when removal of an electron breaks octet or no longer fills the s&p orbital, okay?
So it's unfavorable to remove one from an octet, or it's unfavorable to remove one that you just removed from an octet?
It's unfavorable to remove one from an octet, okay? So it's unfavorable to break an octet or to basically unfill
Since you're happy with little
an
numbers, right?
S&P.
You
Exactly.
take
You
electrons
never,
away from them.
you'll notice sodium, it's okay losing the first electron, but now it has an isoelectronic configuration with neon. The moment we try to take another one away, it's like, no. No. I just got to stability. I was okay with losing one for the sake of getting stable. Not when I got stable. Will you take my next one? Okay. There's a fourth one called electron affinity. I honestly don't know why the AP even includes it in the, it's in the manual that you have to know. They never ask you about it, but quantifies. This is a characteristic that quantifies the atom's likelihood. All right. It sounds really familiar. Attracting an electron by measuring the energy released. I honestly would just know that it's very similar to electronegativity. That's all I would know. It is very similar to electronegativity. That's the big idea. If they say electron affinity, just think of it as electronegativity. All right, and that's all for your lecture.